Okay, so two papers land this year, totally different fields, and they point at the exact same wall.
Right. One says you can run a language model on basically three numbers, -1, 0, 1.
And the other one mathematically proves, that no model ever, no matter how big, gets to be perfectly reliable.
Which, at first those sound unrelated.
They're not. That's the whole episode.
So let's set it up. For years, the industry's whole religion was scale. Bigger model, more data, more parameters, loss goes down, everybody's happy.
The chinchilla stuff, yeah.
Exactly, the scaling laws. And the assumption baked into that was, implicitly, if we just keep going, eventually the errors go away. Hallucination is a bug we scale our way out of.
Which turns out to be, just not true.
Not true. There's a 2026 paper, Majumdar, that derives what he calls a reliability ceiling. Every task has one. It's set by the entropy in the task itself, not by how big your model is.
Wait, so it's like some questions are just inherently fuzzy and no amount of brain power fixes fuzzy?
Kind of, yeah. Math proofs, code, high ceiling, because there's a verifiable right answer. Open-ended summarization, creative stuff, low ceiling, because the ambiguity is baked into the question.
Okay, so that's the reliability side. But then there's this totally separate thread about models getting smaller, like absurdly small.
BitNet B1.58. Yeah, let's get into it.
So walk me through it. Normal models use these 16-bit floating point weights, right? Huge continuum of possible values. Right. And that requires actual floating point multiplication, which is expensive. It's the thing GPUs burn most of their silicon on. And BitNet just throws that out? Pretty much. Every weight gets forced into one of three states. -1, 0, or +1. That's it. That's insane. How do you even train something like that?
So this is the non-obvious part. It's not compressed after the fact. It's trained natively that way from scratch. There's this function, absmean, that scales the weight matrix and rounds everything down to the nearest of those three values during training.
Huh. So the model never even gets to know what a decimal is?
Basically, no. And the reason the 0 matters so much, it's not just binary but with an extra option. The 0 lets the network prune connections. It can just turn a weight off entirely.
So it's building its own sparsity.
Its own sparsity, dynamically, yeah. And because everything's just -1, 0, 1, multiplication becomes its addition, subtraction, or skip. No multiply circuit needed at all.
And that's where the energy number comes from?
That's where it comes from. 71.4 times less energy for the matrix math compared to standard 16-bit. And past about 3 billion parameters, it matches full precision models on actual task performance.
Okay, hold on. That's the part that gets me. It's not worse?
It's not worse, which is, that's the real finding here. It suggests the actual information content of language, the stuff the model needs to represent, is way sparser than we assumed. We were spending all that floating point precision on basically nothing.
So, loop back to the reliability ceiling thing. How do these connect?
So here's the thing. They're the same constraint viewed from two angles. Majumdar's ceiling says there's a floor of irreducible error you can't scale away, because the entropy's already in the task.
Right.
BitNet says, going the other direction, there's a floor of precision you don't need, because the entropy in the weights is already fully used at like 1.5 bits.
So it's both are saying, here's where the actual information is, and everything past that is waste.
Exactly. Compression finds the floor from below. The reliability ceiling finds it from above. Same wall.
That's a genuinely cool reframe. Intelligence has like a bit cost, and you can't cheat it in either direction. So what does this actually mean going forward, like practically?
A few things.
1, hardware. If ternary weights are where things head, current GPUs are massively overbuilt. All that floating point silicon is dead weight.
So we get chips that just do addition, basically?
Basically, yeah. ASICs built for ternary math specifically.
And the reliability side?
The reliability side changes how you deploy things. You stop chasing make the model never wrong and start asking, for this specific task, what's the actual ceiling? And are we near it yet?
Which is a more honest question, honestly.
It really is.
And there's a darker flip side, too. If these tiny compressed models get this capable, that same efficiency is what lets powerful models run offline, on a device, no one watching.
Yeah, that's a real open problem, not a side note.
So less precision, more honesty about the limits. That's the trade.
That's the trade.
I'm Nova,
And I'm Alex.
and this is Code and Cosmos.